Okay, in this video we are going to look at the practice quiz for bonding, and this is what you will be working on in class on Monday to get you ready for your bonding quiz on Tuesday. The bonding quiz will cover both ionic bonding and it will also cover covalent bonding with Lewis structures and molecular geometry shapes. Okay, so let's take a look. All right, first thing, we're supposed to write the electron configuration for the ion that phosphorus will form using orbital notation. And we're also supposed to write the electron configuration for the ion that aluminum will form using standard notation. So this kind of brings back electron configurations, so you got to know that. Please pay attention to the word ion. On a concept quiz I gave in class, several of you missed that you could write the electron configuration for the atom, but both of these are looking for the ion. So before I flip to the next screen, you need to locate phosphorus on the periodic table. So phosphorus should be in group 15, which means it will make a -3 ion, which means it gains 3 electrons. So when you're making the ion for phosphorus, figure out what you need to do to alter the electron configuration of the phosphorus atom. So phosphorus is a -3 charge, and then aluminum, the ion that it will make, if you locate it on the periodic table, it's in group 13, so it will make a +3 ion, which means it loses 3 valence electrons. Okay, so on this slide I have the orbital notation for the phosphorus atom here. So phosphorus ends in 3p3. So it's 1s2, 2s2, 2p6, 3s2, 3p3. Okay, and that's the phosphorus atom. So for the phosphorus ion that makes a -3 charge, it's going to gain 3 valence electrons. And the whole point of forming ions is to achieve chemical stability, which means the atoms will form ions that will look like noble gases. So in order for phosphorus to look like a noble gas, it needs to gain 3 valence electrons, and that's what the -3 means. So it will gain 3 valence electrons here, here, and here. And if you look at your periodic table, the atom that ends in 3p6 for its electron configuration is argon. So when phosphorus makes an ion, P with a -3 charge, its electron configuration will now look like argon, which is chemically stable. Okay, so this structure right here, is the electron configuration for the phosphide ion, for the ion that phosphorus forms. Right, next question. Write the electron configuration for the ion that aluminum will form using standard notation. So aluminum's electron configuration in standard notation is 1s2, 2s2, 2p6, 3s2, and 3p1. And it looks like this in terms of its orbital diagram. Okay. Aluminum makes a +3 ion, which means 3 electrons are lost. So if aluminum is to lose 1, 2, 3 electrons like that, it would look, what is remaining would look like the neon atom. So in order for aluminum to achieve a stable octet, it needs to lose 3 valence electrons. Okay, so it's going to lose the electrons that are 3s2 and 3p1. So its configuration for the ion of aluminum will be 1s2, 2s2, 2p6. So these will go. And then what you're left with is the ion for aluminum that, from an electronic or electron standpoint, looks like an atom of neon. Okay, so just keep in mind when you're asked to find the ion, figure out, well, what charge is this atom going to make when it makes an ion? And then what does that mean? Negative means you gain valence electrons. Positive means you lose valence electrons. And you're gaining or losing so that the electron structure will look like a noble gas. Okay, now we want to use dot diagrams to show the ionic bond that will form between strontium and bromine. And then we're supposed to write the formula and the name of the compound. So with ionic bonds, you're drawing the dots and all that, but you're not showing shared pairs of electrons. So you're not showing single, double, and triple covalent bonds. You're showing how positive ions and negative ions are formed and how they'll attract each other. So strontium is in group 2, so it will have 2 valence electrons. Bromine is in group 17, so it will have 7 valence electrons. So when strontium makes ions, and metals are going to make positively charged ions, strontium will make a +2 ion, and bromine will make a -1 ion. So strontium will lose both of its valence electrons, and bromine will gain 1 valence electron. So strontium will lose this valence electron to bromine, and so now this bromine is a -1, but strontium needs to lose the other valence electron, so you would need to add in another bromine atom, and now bromine this bromine also has a -1 charge. Strontium has strontium has a +2 charge because it lost 2 valence electrons. When you're making an ionic compound, all of your charges of your ions have to balance out to 0. So mathematically, if you think about this, if you have a +2 plus a -1 plus another -1, which is exactly what I have here, +2 and then 2 -1s, then mathematically that sum is equal to 0. So the charges completely balance and cancel each other out. So the formula of this compound is going to be Sr, and I'm not going to write the subscript of 1, I'm just going to leave it, is understood Br2. I have 1 strontium ion and 2 bromine ions. So Sr1, Br2. Also, more importantly, strontium makes +2 ions and bromine makes -1 ions. So I need 2 of these -1s for an overall -2 charge to balance out the +2 charge. And then to name an ionic compound, I don't know if I can do this with my mouse pad. Remember, it's just the name of the metal followed by the root of the nonmetal, and then you add the ending IDE. So this is going to be strontium bromide. Let's see if I can do this. So the most important thing, and this is again review, you have to know how many valence electrons are in an atom based on the position of the atom in the periodic table. You have to know that. And you would also need to know what the charge of the ion will be when the atom forms an ion. And if you understand those two things, then these Lewis dot structures for ionic compounds will become much easier. Okay, so there's that. So you can expect tomorrow on your, or Tuesday on your quiz, a question like 1, 2, and also like question number 3. Okay, so if you have questions about that, ask me in class. All right, so then now we're going to get into drawing Lewis structures for molecules. And molecules, remember, are covalently bonded atoms, and they only involve non-metals. Okay, so we're going to draw the Lewis structure for the molecules, and then based off the Lewis structure, we're going to assign their geometries, their shapes. So if you remember from the previous recording, in order to draw a Lewis structure, first you need to determine the number of valence electrons for all the atoms in your molecule. Then you'll add that up, get your total valence electrons, then divide by 2 to get your pairs. Those pairs must be represented in the molecule in your Lewis structure. Second, single bond all of your atoms and then satisfy the octet except for hydrogen and boron. Hydrogen will make one bond only, one single bond. There will be no lone pairs of valence electrons on hydrogen. Boron will make 3 single bonds only. There will be no lone pairs of electrons on boron. Okay, so let me say that again. Get your pair count, single bond all your atoms, satisfy the octet for everything except for hydrogen and boron. Lastly, do the pair count. If you have exceeded the number of pairs of electrons that can be in your Lewis structure, then there must be a double or a triple bond present. And so we need to show that. All right, so I have PCl3 and CO2. All right, so here we go. So you can draw your Lewis structure for PCl3 like this or like this. And you can move the position of these chlorines. It doesn't matter. Based off of the Lewis structure, then you have to decide a geometry. So if you look back to your orange sheet, and that should be in front of you, you'll have 1, 2, 3 bonded atoms to the central. So my 2 choices for 3 bonded atoms are either trigonal planar or trigonal pyramidal. Since I have this lone pair of electrons on the central atom, it is going to push the bonded chlorine atoms closer. So this is not going to be a planar structure. This is going to be a pyramidal or pyramidal structure. Okay, so that's going to be a trigonal pyramid. And you need to make sure that you understand the differences between planar and pyramid. And really, it's just lone pair of electrons. Okay, next, carbon dioxide. So after you draw your Lewis structure, you do your pair count, you realize that you'll need 2 double bonds. Okay, now I have a central atom carbon, and on that central atom there are 2 bonded atoms. And more importantly, there are no lone pairs of electrons on the central atom. So those bonds are going to try to be as far apart from each other as they can be. And that will work when they are 180 degrees apart from each other. And so 180 degrees indicates that you have a line. So this is going to be a linear molecule. Next, I need to draw formaldehyde, which is CH2O, and I need to draw carbon tetrafluoride, which is CF4. So the formaldehyde, the CH2O, you can draw any of these Lewis structures. I was showing you these because I wanted you to understand these molecules, the way you draw them on your paper, are flat, but really they're in a 3-dimensional world. So it depends on how you're looking at the molecule 3-dimensionally, how you would draw your Lewis structure. All of these Lewis structures are identical though. So any one of these would give you the credit for the Lewis structure. Then you need to decide what's the geometry. So now I have 1, 2, 3 bonded atoms to the central atom, right, on all of them. But if you'll notice, your carbon does not have lone pairs of electrons on the central atom. So it's got 3 bonded atoms and no lone pairs of electrons on the central atom. That means you're going to have, your 2 choices are trigonal planar or trigonal pyramidal. And this is going to be trigonal planar because there are no lone pairs of electrons on that central atom. So those bonds are going to be able to get as far away from each other as they can. And when they're as far away from each other as possible, you're looking at 120 degrees of a bond angle. Okay, so that's going to be a planar structure. And then last, you have CF4. Okay, so there's your Lewis structure. Now, a lot of people flat think, oh, well, that bond angle is 90 degrees. But remember, this is flat on paper that you're looking at the Lewis structure. If you were to build CF4 with a modeling kit, you would see that it's not a flat structure, it's three-dimensional. So this is the shape it would make with your molecular modeling kits. So this structure is going to be tetrahedral. Remember, tetra means 4. So when you have 4 atoms bonded to the central atom and no lone pairs of electrons, then you're going to have a tetrahedral structure. All right, next, draw Lewis structures for all the resonance structures of the carbonate ion. So in the practice before this, we did the nitrate ion, NO3-1, and looked at the resonance structures for that. So this is going to be similar. Remember, when you're doing your count for your valence electrons, you would do carbon, oxygen, and then that -1 charge. So carbon, I have 1 carbon atom in my polyatomic ion, but each carbon has 4 valence electrons. Then oxygen, there are 3, but each oxygen atom has 6 valence electrons. Then the -1 charge tells me I gained 1 electron. So when I do my pair count, I'd have 4. I'm sorry, that should be a -2. Here we go. 4 plus 18 plus a -2 charge. So total, that's going to give me 24 valence electrons, or 12 pairs that I need to represent in the Lewis structure. Okay, so let me So here is your carbonate ion, and you could start with any of these 3 structures, but recognize the fact that you have this double bond between carbon and oxygen. And that double bond is really not truly a double bond, it's a hybrid bond. It's sort of in between a double and a single bond. So because that's a hybrid bond and the electrons are not locked or fixed into that position, you can represent the bond this first position, the second position, or the third position. Okay, so there are your 3 resonance structures for carbonate. As many different places where the double bond can be shown, or where the hybrid bond can be shown, that's the number of resonance structures that you'll have for your molecule, or in this case for your polyatomic ion. Next question, which of the following molecules is most likely to have bond angles of 120? You may need to draw a Lewis structure to determine your answer. When I give you a note like this, just cross out the word may. You need to draw a Lewis structure, okay? Make sure you get it right. So again, you don't have to understand, you don't have to know bond angles. Bond angles will help you recognize something a little bit better, but I'm not going to require you to write or memorize bond angles for the molecular geometry. What I do want you to see is this is the ball and stick model of a molecule, and notice how it's flat. There's nothing like behind the structure, there's nothing coming out of the structure. It's a flat structure, meaning that there are no lone pairs of electrons on that central atom. Okay, so if I were you, I would strongly tell you to draw the Lewis structures for your choices and then pick. All right, so if we start with A, BF3 is going to look like this. And that's your answer, because you have central atom, 3 bonded atoms, but no lone pairs of electrons in the central. NH3 is not a bad choice, but it's the wrong choice, mainly because you've got this lone pair of electrons on the central atom. And as such, it will push these bonded electrons closer together. So your bond angle is no longer 120, because now you've got this extra lone pair electrons taking up space. It's more like 107.5 degrees. So B is wrong. C, I have central atom and then 4 elements or 4 atoms bonded to the central atom. And you could draw it like this, flat, or you could try to show the geometry of it. But that's a tetrahedral shape. And so you're not going to get just 3 bonded atoms here. You'll have 4 bonded atoms. And then the last one, HCN. So you have a central atom and then 2 elements bonded to the central, but no lone pairs on the central. So 2 bonds, no lone pairs on the central. That's going to be a linear structure. So D is out. So your answer there is A. And remember, boron is an exception to the octet rule. It only needs 3 single bonds to be chemically stable. Next, draw the Lewis structures for each of the following compounds and label their geometries. So I did this a couple of different ways. So H2O, you can draw like this. H2S, you can draw like this. OCl2, you can draw like this. Here's another picture if you like that one better. And if to the person who does not know their VSEPR geometry, you would just say, oh, well, that's a line. These are all linear. They're not. They're all bent. So what's going on is you have 2 bonded atoms to the central atom, so 2 bonded atoms, but I have these lone electron pairs here and here. And if you kind of redraw your structure, think about it like this, these lone pairs are going to take up space, and because they take up space, they're going to push these bonded pairs closer. So instead of having a line, you're going to have an angular or bent structure. So these are all going to be bent. Okay, same thing for the hydrogen sulfide, the H2S. It's bent, and same thing for the OCl2. It's bent as well. So its bent structure look like this. And I'm not going to draw all the little chlorine valence electrons, but each of them, well, I will. Each of them will have 8 valence electrons up. Okay, so they all have a bent structure. Okay, last question. You're supposed to classify each particle as an atom, an ion, a formula unit, or a molecule. So atoms, you're just looking at like a single atom, no charge. Ion, you can either be a polyatomic ion or a monatomic ion. Ions are going to have a charge, so look for that. Formula unit is the simplest unit of an ionic compound, so you're going to look for metal, nonmetal, or metal polyatomic ion. And then molecule is going to be non-metal atoms bonded together with no charge. The only charged thing in this list are your ions. Okay, so if we look at A, I have MgO. So Mg is going to be a metal, O, non-metal. Metal, non-metal, no charge. So that's going to be a formula unit. Y'all, I can't write like this. Let's see. Okay, Cr. Cr, no charge, no other atoms there, so it's not going to be an ion. It can't be a formula unit because it's not bonded to anything. It's not going to be a molecule. Again, it's not bonded to anything, so this is just a single atom. It's going to be an atom. SO4 minus 2, boom, that minus 2 charge right there tells me that I'm an ion. And it can either be, this particular ion is a polyatomic ion. Whereas the next one, Li plus 1, so it's an ion because I have a charge there, but there's only one type of atom present, so that's going to be a monatomic ion. You don't need to know that. That's just for your edification. All right, and last, CH3F, so there's no charge, cannot be an atom, sorry, cannot be an ion. There's more than one atom, therefore it cannot be an atom. And if I look in my formula, there are only nonmetals present. So molecules only involve nonmetals, not metals. So this is going to be a molecule. And that concludes your practice quiz. So to get ready for your real quiz on Tuesday, you need to do your practice quiz, watch this video and the last one that are posted on YouTube, and you need to do KIA Quiz 8.2. The KIA quiz is due Monday night at 11:59 p.m. The in-class quiz that deals with all the types of bonding, ionic bonding and ions and Lewis structures, covalent bonding, VSEPR theory, that quiz is in class on Tuesday. And your test on all of this is Thursday the 22nd. So we'll talk more about that in class. Have a great weekend, and I will see you on Monday. Thanks.